I just ruined the microphone. May I start my lecture? I'm very happy to be invited by Arena to give this lecture, and I'm very happy to be first time actually at Masdar and see the activities here, and I talked already to many people. I'm standing here because the talk is videotaped, so I hope I'm not in your way, and you can see on either screens what I want to present about. I must admit that the title is a little bit misleading. I'll talk maybe 10 to 15% about the specifics of the Gulf region, and most of the time I'll spend to talk about my personal research field, which is a new form of photovoltaics, organic photovoltaics, and I personally believe that it's in the long term the future technology for PV, but that is maybe a very biased statement because I'm personally working on it. Okay, before I start talking about science, let me tell you a little bit more about where I come from, KAUST. I'm pretty new at KAUST. I started there in October, so I'm not the expert to tell details, but my outline will be that I'll talk about KAUST and the solar center I'm heading. Then I'll talk about research centers, research topics at the solar center, and the last 2/3 or 60% of the talk will be organic solar cells. This is one of them, and you can already see a point. They are flexible, they can be transparent, and at the end they should be all carbon. Now, KAUST is actually, in a larger context, the king of Saudi Arabia has decided to establish 6 economic cities, and together with them a science and technology university. And the science and technology university is KAUST, which is about an hour north of Jeddah at the Red Sea. And one of the economic cities is right next to KAUST, and it's just starting. The economic cities are not that far as the university, which is pretty much completed. Now, KAUST started, was actually the decision to fund it was made in, or to start it was made in 2006. The construction was started in 2007, and the university was completed in 2009. And it's right at the border of the Red Sea, and indeed this is a photograph from the site of KAUST it says August 1st, 2007. And then for 2 years it was actually the largest construction site in the world, and within 2 years basically the university was built. Now I must get myself a little bit oriented. This is the harbor, and the basic university buildings are those. There are 5 big buildings which host the laboratories and the facilities, and these are the central lecture room. This is the library and cafeteria area, and this is housing. KAUST has also a huge housing because most of the faculty live on a campus. And the solar center is actually in this building, building 5. And my office is here at this corner, and I have a beautiful view over the Red Sea, which is quite nice. To give you a few numbers, at the moment KAUST is 120 faculty and 700 graduate and PhD students. There are no undergraduates. The campus at the moment is 50 square kilometers. It is constantly growing because there should be additional industry. The very unusual point about KAUST is that it's not dependent on continuous funding by the Saudi government, but instead the king made a multi-billion-dollar endowment, which is not in the country, which is not in Saudi Arabia, but it's managed and located in the United Kingdom. So KAUST is financially and politically actually completely independent of the Kingdom of Saudi Arabia. And also quite interesting and surprising is that the king made, in my opinion, a wise decision. He let Saudi Aramco build and manage it, and Saudi Aramco knows how to build cities in the desert, and that's the way they achieved it in 2 years. But this summer actually this will end, and that KAUST will be under its own management. As said, I think it was a smart decision, but the paperwork of a big oil company is sometimes a hassle compared to the paperwork of an average university. Now the way KAUST is organized is in research centers, and it's a pure science and engineering university, and the main topics are clearly water, energy, desert agriculture. There are 9 different centers, and the solar center, solar and photovoltaic engineering center is one of them. What's the vision of the solar center? Clearly it is devoted to research, to basic research. We are not under big pressure to do applications. We should do basic research. And the 3 topics we want to work on is photovoltaics, energy storage, and energy conversion. At the moment we concentrate on photovoltaics. One of the most important points is that we want to bring scientists to Saudi Arabia, locally trained scientists, and not the key mandate, but we also take it seriously, is to work with local industry. For the moment we concentrate on photovoltaics. We have a very active program, and we publish with a high rate already in good journals on photovoltaics. We call it all emerging photovoltaics, novel technologies like organics. I'll concentrate on that today, but also quantum dots. CIGS is, so to speak, the most established technology we have in the lab. But we also work on electrodes, coatings, optics, and one key topic is actually, and that is where it's relevant for the Gulf region, dust mitigation. So we work on coatings and cleanings also in framework of a spin-off. In the mid to long term we will also work on storage and conversion. And the storage we have already a small but quite interesting program on direct solar hydrogen generation. Now this is maybe not that informative, but when you talk about photovoltaics and high efficiency photovoltaics, it's clearly that it's mostly materials physics, simulation, synthesis, but also device fabrication and testing and interfaces play a big role. So these are the main competencies in the solar center. We don't have any PV system competence yet, but we are setting it up now. What's unique? I think there's no other place I know in the world where these emerging PV technologies are investigated in such a breadth than at KAUST. We have, as said, organics, perovskite oxide, quantum dots, and CIGS. And another specialty we work on is that many of these systems we deposit can be either deposited in vacuum or by printing from liquid phase. Vacuum is good for research, printing is good for low cost, and therefore we have nice comparisons. The history is that the solar center was approved 4 years ago. It took a couple of years to finally also fill the labs, and I started last October. In April we have an inauguration, and we organize a yearly conference, and the next conference will be in November. We try to stimulate spin-offs. I'm actually, from my home university of Dresden, a very active entrepreneur. I've founded 8 or 9 companies so far. And there are 2 in the center. One I want to cover a little bit more in detail. Nomad is on cleaning of modules, and the other one is a nano assembly company. We are at the moment 8 faculty in the solar center. I'll cover the work of some of them in some more detail. We are constantly hiring people. We have one, I would say, spectacular new hire for those who are in the field of organics. Jean-Luc Preda from Georgia Tech will join KAUST this summer. So KAUST is now able to attract #1 top worldwide researchers. One of the specific topics we work on is that we want to combine these different emerging PV technologies which have these attractive features to also achieve high efficiency. You know, silicon is today at 20 or more %, and we want to make tandem cells of these different technologies. So we want to combine organics with quantum dots that we have already done. We currently combine CIGS with organics and many more of those approaches. In organic PV, we have already an activity since years from Aram Amassian. He graduated in Canada and is since 5 years at KAUST, and has very nice results on organic PV. One of his main topics is to investigate the basic science of coating technologies. For instance, in this experiment, the lab technique is spin coating, the mass production technology is blade coating. if you take the spin coating recipes, 6.5%, and simply do plate coating, you get a non-functional cell. But by doing the right plate coating, he could match the spin coating by really understanding the basics of the morphology. I don't want to cover that in detail. And he works also on quantum dot solar cells, where he has achieved more than 8%, which is among the best values in the world. There's work from Pierre Bourjuge, who is a synthetic chemist from Berkeley, doing new molecules, but also doing devices and tandem cells. Osman Bakr is a very interesting person. He's Saudi himself, and he actually grew up right on the campus of KAUST as the son of a fisherman. But later on he went to Harvard and MIT, and is now back as professor on the place where he was born. He works on quantum dots. He has novel technologies to do high efficiency synthesis of quantum dots and high quality. But I can't really cover that in detail. Omar Abdel Zabur is trained all over the world, was working with Ahmed Suhail, the Nobel Prize winner, and works on ultra-fast spectroscopy. This is one result, again a very basic research result. He looked at carrier generation in exciton generation in quantum dot structures, and the very nice effect he saw is that in these structures you generate multi-excitons, and in some cases he had 160% quantum efficiency, so almost 2 excitons per photon were generated. And finally, Udo Schwingenschnögl is a theoretician from Germany who works on density functional, does the theoretical calculations, band structure calculations. And we have extensive labs. Solar Center alone has 3,000 square meter labs, including a 1,000 square meter clean room, with a very large number of tools. I would say we are over-equipped at the moment. The one thing I learned already when I came in the first days, KAUST is the best equipped university in the world in terms of tools, no doubt. And my task is now to get all these tools into use. Okay, that was what I wanted to say as an introduction, and now a little more to my personal research. And most of the results I'm now presenting are actually obtained at Dresden, because I'm new at KAUST, and I personally don't like to talk about results of other people. So this is, I should make clear, mostly results which are not from KAUST, but I'm quickly setting up a group, and we will continue that work in KAUST at full speed. So I'm acknowledging people from the University of Dresden here in this list, the institute which I'm heading in Dresden. Then a spin-off company, Heliatech, which we founded 7 years ago, which is producing now, pilot producing modules. People from University of Ulm who supplied molecules, and people from Max Planck in Mainz who did theory. Now, I'm not sure whether you know much about organic semiconductors, but many of you carry it in the pocket. If you own, for instance, a Samsung mobile phone, a Samsung Galaxy, it has an organic LED display. And actually, every Samsung phone sold generates also a little bit of money with our spin-off company, Novalet. So I'm very happy whenever I see a Samsung phone. And this is now small displays, but the OLED television is coming as well. At the moment, such OLED televisions cost $10,000, but they will get cheaper very soon, and the display quality is superior. OLED lighting is another approach to make high quality light. It's not really commercial, and same holds for OPV. At the end, there will be also organic electronics. This is a display demonstrator which contains 1 million of organic transistors, actually done by Plastic Logic in Dresden. But these are technologies which are still in the baby stage, so to speak. Organic PV has a large potential, there's no question. As you can see, it's flexible. It can be transparent, homogeneously transparent. It can be almost any color. So, for instance, for building integration, it is ideally suited. It's basically mostly carbon and should use very little material and energy, which leads to a short payback time. So, in principle, it's very attractive. However, you know this chart maybe, that's the most important chart in PV. It's actually the efficiency of solar systems versus time. And the most important data point is exactly this one. This is crystalline silicon, University of New South Wales at 25% lab efficiency. And that's the market at the moment. And as you can see, organics is still, I call it in the noise down there. But the surprising thing, and I'll show it in more detail, is that the gradient, the increase with time, is actually the largest in this field, and that's why I believe that organics is promising. But efficiencies are still low. As you know, photovoltaics is in a learning curve, and in the last few years, spectacular. It actually crossed the long-term average and became much more rapidly cheaper than previously. And we have seen now prices below €1 per watt peak, which only a couple of years ago was nobody predicted. So the question is, how can organic PV compete to this curve? This is the silicon learning curve. For that, I show you a paper published a couple of years ago, which simply does a cost estimate of dollars per square meter for organics. And as you can see, they have a low and high cost prediction, but the basic message is that somewhere between about $20 to $40 per square meter. Now, the key question is then the efficiency. If you have 10%, you get about 100 watts out of a square meter, and then you would be at 23 cents to 37 cents. If you get, say, 20%, then you would be at 11 or say 18 cents, and if I go back one slide, you would be even below the scale here. So at least potentially, if we get high efficiency, organic PV can beat silicon, but the question is, can we get these high efficiencies? And the other point is energy payback, and this is a publication from Annick Antier and collaborators who calculated energy payback. This is the amount of energy, megajoule per watt peak, you need. And I plotted here a dashed line, which is the harvest per year in Germany. In Abu Dhabi, you would definitely be a factor of 2 and 2.5 above it. But the basic message is that most inorganic PV systems, at least in Germany, have several years of energy payback time still. Whereas organics, these curves are organics. If you are in a range of, say, 5% or so, it's already in Germany only 1 year. But if you go, say, to 10, 15, or even 20%, this curve goes 1 over x. You can get energy payback times even in Germany, which are 2 months or so. So the potential for a very short energy payback is there. Again, it depends on the efficiency. Now, when you calculate the efficiency of for single junction solar cells, that's a calculation done by a PhD student of mine, you basically end up with an efficiency which is on the range of about 15% here. If you have the optimum gap, then you end up with about 15%, which means that in a module you would expect 10 to 12. And that is too little. So obviously, if you do organic solar cells, single junction, you have a problem. So the way to go is then, as you know, to go to multi-junction. This is a graph I took from a recent paper of Michael Gretzel. If you have a single junction device, you harvest the spectrum, but in the higher parts you lose a lot of energy. And if you divide it in 2 or 3 or 4, you can increase the potential efficiency. The Shockley-Queisser limit for a single junction is 31. If you do 2 junctions, a tandem, 42. If you do 3, 49. If you do infinity, 85. But nobody can do an infinite number of junctions. So the way to go is from a single junction to a tandem or triple. And I will show you later that in organics this can be quite easily done. And then if you do again a very reasonable estimate of efficiencies, you end up for optimum gaps at about 21%. And that is my personal motivation. I want to reach these 20–21%, say in hopefully in a decade or so. And then if the cost is also down, we have a killer product, and maybe we can beat silicon in the long term. We'll see. Silicon has been a very difficult contender in PV to beat, and it will stay like that. This is now the enlarged graph of this NREL plot, showing the lower right corner. And the main message is that organic PV started with work at Kodak, Qingtang in 86. And for the long term, there was only small area cells, but in the last few years, we've also seen larger area certified cells. And as you can see, the development has been enormous, and Heliatech, which is in conjunction with my home institute, the world record holder, is now at 12%, which is approximately equal with the dye-sensitized cell and the amorphous single layer. So they are all on the same level. As I'll show you later, this graph is misleading because it measures the efficiency under standard conditions, and the real harvesting outdoors is actually for organic significantly better. These 12% are almost 15% for silicon. Okay, now I come to the second part of this organics part. I will talk a little bit about materials. And the following 20 minutes or so are pretty technical. I presume that the audience is quite mixed. So if you don't know the details or don't understand it, don't worry. I'll wake you up once I'm finished with the technical part. And this is more for the people who have a detailed knowledge. Now, if you look at an organic solar cell, it's actually a somewhat more complicated device than a silicon solar cell. The main reason is when you have the absorption process, you generate excitons, bound electron hole pairs. And in silicon, they separate immediately, but in organics, it is not easy to separate them. So first you transport an exciton, then you separate it, and then you transport charges and attract them. And the way to separate this, I'll come back to that in a later slide, is that the exciton, the bound electron hole pair, has to travel to a boundary between two materials. And there's an energy step at the boundary so that the electron will fall down and the hole will stay here, and that separates the exciton. And unfortunately, the distance these excitons can move is small. It's on the order of 10 nanometers only, which is much shorter than the absorption length. So what you do is you mix these two materials in a so-called bulk heterojunction. So you have a nanomorphology with different paths. And this nanomorphology is the big challenge, to control that and optimize it. Here are some data for the diffusion lengths. We've measured some by modeling in an organic material. And the best fit is 10 nanometers. So these excitations can move only a very, very small distance. In silicon, they can move hundreds of microns. And the second problem is, as I said, the tightly bound exciton. This is the spatial coordinate, and this is energy. And an exciton in silicon or gallium arsenide is very large, about 20 nanometers large. And the binding energy, this is KT, room temperature. The binding energy is very small, whereas the organic exciton is very tightly bound and very small. So it's hard to separate. And as said, the way to separate is a heterojunction, and to combine with the short diffusion length, the ideal solution is the so-called bulk heterojunction, where you mix the two materials. And typically these domains should be on the order of 10 nanometers or less. And that is actually very difficult, first of all, to achieve this morphology. Secondly, to characterize it and control it. Now, that leads to the point that the requirement for the materials are complicated. We need materials which form these such a network which can transport carriers very well. We need to adjust the domain sizes. And at least for organic materials, we need fairly high mobilities. 10 to the minus 3 is already a quite high mobility for a disordered organic material. And I will show you the one materials class we worked on. We worked on thiophene derivatives. We call it the Thiophene Zoo because there are many, many animals in that zoo. We actually did a quite systematic variation. As you know, organic molecules are plenty around. Mankind knows about already 10 million organic molecules. And what we did is we looked at these thiophenes, and we varied two things. We varied the number of thiophene rings in the molecule from 3T to 6T. And we varied the side groups. There are certain side groups in either molecules with hydrogen, methyl, ethyl, or butyl side groups. And this way you have a beautiful handle, because with this coordinate you change the energetics of the molecule, and with this coordinate you change the crystal packing. And for instance, the energetics, you can nicely see that when you change the length of the molecule, the highest occupied orbital, the HOMO, is dramatically shifting upwards for longer chains, whereas the LUMO has a much smaller shift. So you change the gap from the blue to the red, and you can change for the step where the exciton is separated. This energy level is really relevant, and therefore we could really systematically look at the energetics. I want to show you one example where we compared a number of molecules. We compared these 3 molecules, and as you can see, they have only very minor differences. The only difference is that the methyl groups in this molecule is in different positions of the molecule, and specifically I'll look at this 1155 and 33 molecule, where in one case the methyls are at the center and the other case at the outermost thiophene rings. If you do absorption spectroscopy of these molecules in solution, actually you see that they are almost identical. These are the dashed lines. They absorb in the visible strongly. They are very colorful substances. When you do the thin film here, you see a strong redshift, and you see that there are somewhat larger differences already between these molecules. When you look at the structure, in this case by grazing incidence X-ray diffraction, you again see quite some differences. When you deposit the film at room temperature, it is actually in the material number 1, the 1155, which is most highly ordered. If you, the free compound has the worst ordering, the weakest peak. Now if you do this heterojunction with the other molecule, which is in that case C60, the soccer molecule, you see that, and if you go to a somewhat higher temperature, which we do for better domain formation, you suddenly see that things turn around, and now compound number 3 looks best, shows the most strong diffraction features. So initially our argument was, okay, if we want to do the solar cell, which is this film, and this temperature, compound number 3 should be the best one. And indeed, with this compound number 3, we achieved over 7, or in more recent measurements above 8%. So for a single junction organic solar cell, also calibrated, I should mention, by Ise in Freiburg, this is a very good material. And the other compound, the compound 1,5, which has the methyl groups here at the end, was significantly worse, and we published a paper where we showed that this is better, and we argued this is better because it has the better crystal packing. Obviously, these small differences in crystal in the molecular structure make a difference in the crystal packing. Now, in the meantime, we've learned that life is more complicated than initially thought. We obtained these data because one of my students did measurements at the synchrotron in Stanford, grazing incident wide angles scattering, and again systematically comparing layers of these different molecules. And at room temperature he gets pretty broad reflection, so at room temperatures both these molecules grow fairly disordered, close to amorphous. At somewhat higher temperature, in this case 110 degrees, the peaks narrow, and there seems to be a quite good ordering. But the main difference is when he looked at the blends again of the molecules with C60, with the fullerene, and the main message was that the molecules actually behave very similar, but on different temperature scales. What he found out is that the 3,3 molecule, which we thought is the better one, orders already at lower temperatures than the 1,5. If you go to 140 degrees, the 1,5 also orders very nicely. However, the solar cells we produce typically at lower temperatures, 90 or so, because of processing reasons. And therefore, actually, the main message was that we we concluded this compound to be better only because we were in the wrong temperature range for this other compound. And if you go high enough in temperature, even this compound can pack very well and produce very good solar cells. By that I want to show you how complicated this business is. We have millions of molecules to choose from, and it's very time consuming and difficult to understand their behavior. And most people in the field are working on these new molecules and better understanding. This is another a detailed study where we looked at it, but I'll skip that here because it's getting too complicated. Now I come to the final part of this talk, and I'll talk about the tandem cells and the harvesting. And this is the point where those who do not know X-ray scattering in details can wake up again. And this should be now comprehensible for everybody. So tandem cell, as said, means that we stack two junctions with different absorption on top of each other. And for organic solar cells, this is a little more complicated because the organic solar cells, the total thickness is a few hundred nanometers only, which means that you have standing wave optics in the device. And you need to think about what you do, because you need to move your photoactive layers into the regions where the electric field is as high as possible. And fortunately, we have developed years ago a technology which allows that very nicely. We have developed these N-type and P-type doped organics. In the Samsung phone, actually a P-type doped layer is contained. That is why Samsung is using Novalet technology. But here in the solar cell, it has two advantages. The one point is these layers are transparent, so you can move the absorber layer to the point where you have the highest field intensity by these transparent window layers. And the second point, if you make a tandem solar cell, you know, each generates electrons and holes, and in between you need what we call a recombination contact. You must recombine efficiently the electrons and the holes. If not, you lose voltage. And again, this PN junction, this work on the doped semiconductors, this PN junction helps here very well. I should mention, when we started this work in Dresden in the early 90s about doping organic semiconductors, we had no idea what it was good for. We had no intention to put it in organic LEDs. We had no intention to put in solar cells. We simply thought this is basic research, it's interesting, let's do it. And in my opinion, it shows that it's stupid to push universities into application. You have to do basic research, you have to be curious, and sometimes you discover things which later on have a commercial application you never thought about. And many politicians, even in Germany, overlook that. They always want applications and quick profits, but that's completely wrong. You sometimes just be curious and do things which are interesting. Okay, to show you how these tandem cells work, I'm showing a simple example we did. These are tandem cells which combine one of these thiophene absorbers I've discussed and another material of phthalocyanine, both with C60. Just for fun to mention, these phthalocyanines you see every day. If you buy something blue, either a blue t-shirt or a blue plastic can or so, it's probably dyed with the phthalocyanine. The German Autobahn signs, the blue signs are phthalocyanines. So many of the materials we are using are actually well known commercially as dyes. These as you can see, the two different materials have somewhat different absorption spectrum. The thiophene is again in the visible, and the phthalocyanine in the infrared, although you see there's a large overlap between the two, which is unwanted and which should be avoided. And then we make this PIN cells with the doped layers, and as you can see, these are already 6 or 7 layers, the two cells by itself, or we simply stack the two cells on top of each other. And in that case, you have this recombination junction, which is here, and simply making a PN junction between two materials is producing this recombination junction. Now, as you can see, we have a device which is still very thin. Many layers are only a few nanometers, but we have a 10 or 12 layer device, and the question is how to produce that. And we do that by evaporation in vacuum, and in vacuum it's actually pretty easy to make such a stack. And Heliatech is doing exactly such stacks now in pilot production on a tool I'll show you in a second. And the point is, when you make the tandem, you basically double or you sum up the voltages very nicely. you need to match current, which in this case we didn't achieve very well. But as you can see from the IV curve, which looks pretty rectangular, this works very well. And actually the tandem cell has higher fill factors at 74%, which for an organic solar cell is an excellent value. And if you improve that and optimize it, you achieve what Heliatech achieved now a good year ago as world record. This is actually, when you look at the voltage, you can see it's a triple cell which has been calibrated by SGS and has 12%. This is an intermediate result. In the meantime, Heliatech is a little further, and that's the current world record for organic PV. Now, as I showed you, 12% on this annual chart is still pretty much down. But 12% is better than it sounds. Oh, sorry, I forgot this one slide. When you scale it to modules, the current best values are around 10% on the active area. So it scales reasonably well, and again, you can nicely see different colors are possible. For instance, for building integration, this is very important. Now, why do I say that 12% is better than it sounds? It's something we call the O factor. And the reason is quite simple. When you quote an efficiency in photovoltaics, you quote the standard measurement, which means one sun, 25 degrees and perpendicular incidence. Especially in a country like Abu Dhabi, this is not the case. In reality, you have outdoors 40 to 60 or even more degrees. At least in the morning and the evening, even in a sunny day, you have less than one sun. And if there's haze, like it's often here in these desert countries, or clouds, then you have diffuse light. And fortunately, organics has a positive temperature coefficient. It gets better when it's hot. It has a higher efficiency for lower intensity, and it has actually a super Lambertian behavior for the diffuse light responsivity. And if you take it all together, we have measured in initial tests up to 30% better performance. So in other words, when you take a 12% organic module, it compares pretty well to a 15% silicon module. To show you some data, this is a 10.3% cell produced by Heliatech. This is the standard measurement condition, which is put at 1 for the different technologies. Amorphous silicon, CIGS, and crystalline silicon all go down, whereas the organics is actually at the point where in a hot country in summer, its maximum is then at 55, 60 degrees. And organics gets better by 7-8%, whereas all the other technologies get worse by 10 to 15%. So this is already a huge effect. And if you take the intensity effect, it's the same way. When you go down from one sun, this is, about one sun. Organic goes up significantly. In many cases, it has a maximum around about 0.1 suns. It can be about 10 to 15%, whereas this crystalline silicon and CIGS actually get worse for lower intensities. So again, in the morning and the evening, your organics does better. And finally, there's a small angular effect. Another important point is lifetime. And when I started working on organic semiconductors 20 years ago, I was pretty pessimistic. I didn't expect any good values. But we have learned that it can be quite amazing. This is work from Christiane Falkenberg, who is now with Heliatech, did her PhD thesis with me. She was looking at different electron transport materials, new electron transport materials. She wanted to replace C60. Unfortunately, in terms of lifetime, this failed because the C60 cell had the best lifetime. She measured under a simulator of 2 suns for several thousand hours, and the C60 cell basically did nothing. At the end, she extrapolated because, I mean, typically a PhD thesis in Germany takes 3 years, and she couldn't measure long enough. But after 2 years or so, she extrapolated, and she came to 37 years. This is now not very telling because lifetime is defined as 80%, and extrapolating such a curve to 80% is clearly with a very large error. But I'm showing this slide only to show the sheer number. The lifetimes of these organic molecules can be surprisingly long. Although there is one one point which has to be treated with care, and that is this is between glass sheets. In practice we use plastic substrates where the water and oxygen which degrade can diffuse through glass is absolutely tight. So this is only to demonstrate how stable these materials are. Another point which is not mentioned here in the slide is you need to block UV. If you do not block UV, organics cannot survive that, but that can be done. These are data from Heliatech for a commercially relevant device. It's actually a foil encapsulated flexible module, and this is an IEC standard DMP test, which is treating the modules at 85 degrees temperature, 85 relative humidity. And the standard requires that over 1,000 hours there should be only 10% decay, and the Heliatech module had a 3% decay. So it easily matches already these standard DMP tests. And at the moment the total outdoor lifetime should be on the order of 10 years for such modules, and the goal is in the next few years to get it to 20 years, which is what is typically expected by customers. So at least the perspective is there that organics can reach these long lifetimes needed, but there's still more work to be done, especially these encapsulation foils which are used, these barrier foils. They are at the moment way too expensive, and we have to find cheaper ways to produce them. Now Heliatech is operating a pilot roll coater in Dresden. This is the inauguration of the roll coater. The roll coater is actually this big tool. It was hidden behind a paper wall because the tool is proprietary, like the whole technology. But you can see it's already a very big chunk of iron, and it produces on 30 centimeters modules. Unfortunately, the modules are too large to put them in check-in luggage, and I couldn't bring one over. But it's quite nice to see these flexible modules. There's actually a way to see how the production works, because at the Fraunhofer Institute, where I was previously working, we have such a research tool which is public and we can show. And this shows the principle. It's a big vacuum tank here, and in the door of the vacuum tank you have first of all 2 cylinders which wind and unwind the plastic foil, and then you have a very large cylinder, it's 2 meters large, where you pull the foil around. And what you cannot really see here is around these cylinders you have the evaporation sources, and if you have a sequence of 12 layers you only need 12 sources, and then you pull it once through and all the 12 layers are on the substrate. And this works actually surprisingly well, and this tool from Heliatech here is now operating and producing pilot material, and therefore it is possible to do this complicated multi-layer system in a very efficient way. And just to show you examples, we on this test tool at Fraunhofer we did mainly organic LEDs for lighting purposes, in this case actually on an aluminum foil, and this is a test of the foil, how it comes out of the tool, and then you see that it works nicely, and the technology has been demonstrated. So in summary, the organic PV technology is, as said, a small baby, but I see a large potential for it. Which are the markets? This is again a slide from Heliatech where they looked at different markets. Clearly you could go for mobile electronics, but when you really look at the numbers, it's an insignificant market because the areas are very small. Same is what they call the leisure and comfort market. It could be used for going into business. But for the moment, Heliatech has identified automotive and building integration as the first markets. Especially with automotive, there's a point which is, in my opinion, nearly unbelievable, but which is beautiful for organic PV. In Europe, the European community is putting a lot of pressure on the car manufacturers to reduce carbon dioxide emission. And they have set an upper limit of 100 grams per square meter for, I think, 2020. Now, if you take these tanks people are driving, also in this country, you know, these private tanks where one person having 60 kilos sits in a 2.5 ton car with 500 horsepower. You can't beat physics, you know, you cannot make such a car with 120 grams. But on the other hand, the European community doesn't want to endanger, for instance, the German car industry, so they found a trick. If you put a solar cell, for instance, in the roof of the car, you get a discount. They discount a few grams carbon dioxide. So the automotive industry is now really happy to take the solar cells and put them in the roof. And then the person driving this tank and wasting gas can feel good because he has this solar cell above his head, who in reality reduces carbon dioxide by 0.00001 gram per kilometer, but that doesn't matter. The car is still legal to be produced. So you have to live with that if you work in renewables, but in this case I'm really happy that the automotive industry is helping us. And the second market is building integration, which is pretty much clear. In most modern buildings you have glass facades, and if you can use them to produce energy, it really makes sense. And actually, many people want to produce zero energy buildings, and organic PV, due to its transparency and attractive color, is very nice. Okay, so as a conclusion about this organic PV part, the biggest problem is we still need to break through in efficiency, but the physics are on our side. It's possible. We will need tandem structures to be really competitive. The biggest worry is that the design rules for the materials are very complex, and it's still mostly empirical. And the biggest problem in finding the design rules is that the processing has very subtle variations which we cannot really control. But there are efficient manufacturing technologies, and the technology will be available. And as said, my personal goal is to make, in the long term, organic PV to a viable technology also for power generation. Okay, that's all. Thanks a lot for listening, and I would be happy to answer any questions. Are there questions or comments? Please.
Thanks, Karl. Very nice presentation. Have you tried to correlate? I mean, one of the things that you said, that if there is less than one sun radiation, which is usually the case in most states due to sun, dust, and whatever, your PV, your organic PV, has a higher efficiency. This could, in a way, be an advantageous strategy to counteract sand accumulation. Because the more sand you accumulate, the least. So, have you done a bit of a rule of thumb?
No, we haven't done any outdoor tests with organic PV, but you are absolutely right. A silicon module, if it's dirty, gets down double, because first of all of the dirt, and secondly because the efficiency goes down. Whereas an organic module, if it's dirty, goes down because of the dust, but goes up because of the efficiency. That hasn't been tested, but it should be a measurable effect, and we would love to test it.
The other thing that I was wondering is, you know, that one of the issues you mentioned is to have self-cleaning or coating that reduce the adhesion of sand particles. And one other thing that you said about organic PV is the fact that UV is not something that you like a lot. So have you thought of combining, for example, a hydrophilicity switch or hydrophobicity switch of titanium oxide as a filter of UV, and at the same time gain an advantage in terms of wetting? Is this something that you were looking at? Or? Actually,
I forgot one slide. It wasn't in the talk. I forgot to put it in. We have some super hydrophobic coatings at KAUST, developed at KAUST, which are based on zinc oxide, and they would do exactly this function. For the moment, the solar modules of Heliatech use a commercial UV blocking foil. You know, you can get these for many purposes. You can use it, but you are absolutely right. You could combine the dust mitigation coating with UV blocking coating.
I need to go to Florida. This is the time of stream.
Okay.
Thank you very much, and thank you very much for saying that basic research is important. all of you. See you, thanks.
Thank you. Further questions or comments?
Wonderful presentation. Thank you.
Thank you. Okay. Thank you.